Okay, now we're going live. Okay, welcome everyone to this. I still have one open version of the video somewhere. Let me quickly figure this out and close it. There. Okay, welcome everyone to this week's talk in the 3GD seminar series. It's my pleasure to welcome Andrew Davison. Andrew is a professor at the Department of Computing at Imperial College and also leads the Dyson Robotics Laboratory at Imperial. And he's very well known for his research in SLAM, applying SLAM to related problems. And if you've been working in this area, you definitely know his work, starting with MonoSLAM, integrating objects with SLAM++, dense reconstruction, for example, with elastic fusion, his work on whether it's better to filter or to optimize, and the list goes up. There's a lot of interesting work on combining semantic scene understanding with SLAM that I find very inspiring. And he has also written two very interesting articles about the future of SLAM and spatial computing that are both on arXiv and that I can very much recommend to read. And we also have a panelist here today, Stefan Leutnegger, who is currently a professor at TU Munich and before spent quite some time at Imperial working with Andy. And before that did his PhD in Zurich. And yeah, without further ado, Andrew, the floor is all yours.
Thanks very much. Thanks for the invitation to give this talk. Also thanks very much to Stefan for coming as the guest panelist. So in fact, a lot of the work I'm going to be showing Stefan was also involved with, but also some other stuff that he can ask me, I'm sure, some hard questions about. Okay, so let me share my screen. Great, so let's get started. So so the title of my talk is Representations and Computational Patterns for Spatial AI, and hopefully by the end of the talk you'll have a reasonable idea of what I'm talking about there, but it's very much related to my vision of where this whole field is going. So let's just start with having a bit of a think about where we are now. So this area that I've been working in now for over 25 years of visual SLAM is all about how do we in real time estimate the position of devices that are moving through the world and build some kind of map or model of what's in their surroundings. And 20 years ago, that seemed like a bit of a, that was a tough problem. Not many people were that interested in it necessarily, and especially trying to do it with cameras as the primary sensor. But now, of course, this technology is really out there in products, and here's just a sample of some of the types of products that actually already do visual SLAM. So things like robot vacuum cleaners. This is the one from Dyson that I was personally involved in working on with the team at Dyson. But other companies, including iRobot, have vision-enabled robot vacuum cleaners. There are now SLAM capabilities in mobile phones, things like ARKit and AR Core that enable different applications. There's the SLAM capability in headsets for virtual and augmented reality from companies like Oculus and HoloLens. And then there's also great SLAM capabilities in drones from companies like DJI and Skydio. So what does this technology do? So the most important thing that it does is positioning. So these devices will use their cameras and other sensors such as inertial integration to make mainly sparse maps of features in scenes that they can use to then estimate their motion accurately as they move through spaces. They're also kind of rapidly acquiring capabilities in dense and semantic mapping, and that's all about giving them more of a kind of intelligent sense of the space around them. And this is all progressing now quite fast, of course, in industry and in products. It would probably be true to say, though, that these are still somewhat preliminary products at the moment. So they do certain things pretty well, but they're far from the sort of general capabilities in robotics or assistive devices that I think we'll be aiming for in the longer term. So just to say a little bit about how SLAM has really progressed over the years in terms of cumulative levels of performance. So actually, this is a slide from our startup SLAM core. And we've been using this term spatial AI as a kind of, an image of where we think SLAM is going. And my vision is very much that the general kind of intelligent ability you need to understand space in order to do really intelligent things, whether you're a robot or some other intelligent smart device, that capability is not like something that sits on top of SLAM. I've always thought it's something that I've always been interested in working on, and for me, that all this research in SLAM is gradually evolving into, and the kind of scope of what we call SLAM or spatial AI is therefore always growing. So we've seen this progress through systems that just do robust localization via sparse mapping into systems that now do dense mapping of scenes, and now, coming in very much at the moment, scene systems that actually do semantic understanding of scenes. And I just think this ongoing work in SLAM is very much the right sort of model for making progress in this area towards much more generally capable systems. And in particular, the way we work on SLAM, we build these real-time systems, demos, open source software, code, and things that people can really use and integrate with other things. That's the right kind of model to stick to, I think, if we actually want to progress in this field. So where might we actually get to? I've just got a couple of quick pictures here. So one, of course, is robotics. We might imagine much more generally capable home robotic products in the future. And just to say, this is a mocked up picture I found on the internet somewhere and is no way representative of any concepts I know of real products. But this is a generally capable household robot, but it has to work very well. It has to work within certain constraints to be a useful product. Its price, size, safety, aesthetics, power usage, all of that must be reasonable for this to be a useful product. And here's another product that a lot of people think about a lot, a breakthrough kind of augmented reality product that might become the next kind of major mobile computing platform that might replace the smartphones in our pocket. So if something like this really worked well, did all the computing that a phone could do, but would also provide you with this kind of smart overlay of information onto your vision that would come on and off as needed. I think if that existed, that could easily become the next big computing platform that everyone would use. But remember just how tough this is to make. So what current headsets for AR are like. They're really cool, but they're still a bit kind of clunky and heavy. The battery life's not very good. And they probably only do a fraction of the things you would really want them to do. So if we're aiming towards this general product, which for instance might have to weigh 65 grams and have all day battery life, that's really, really tough. But those are the sort of things that I think we're working towards. So just to make that clear, I think there's a large gap to close. So first of all, I think whether you're working in robotics or whether you're working in something like AR, the sort of capabilities you want from this SLAM or spatial AI system are probably quite similar. You want something that will build a representation of the scene and smartly understand everything that's going on in that scene. This is tough. These products don't exist yet, not because there's no demand, but because we don't know how to build them, and certainly not within the constraints that they will have to be built within. We've got current products that exist. We've got stuff going on in research labs, like our lab or in industry. But then there's a big gap to close between that and where we actually need to get to. So as Torsten kindly mentioned, I've been thinking a lot about the sort of general progress of this field, and I've written a couple of papers that you might find interesting. So these are really like discussion position papers, future mapping. So far there's 2 of them. I'll mention the second one in a minute, but there might be more at some point. In the first paper, that's called The Computational Structure of Spatial AI. And really there I make some kind of some hypotheses about this general area of spatial AI. And a couple, 2 of the hypotheses are a spatial AI system to enable embodied AI should build a persistent and understandable scene representation, which is close to metric 3D geometry, at least locally. So I think if you want a generally capable, something like a robot that could, tidy up a room, I think it needs something a bit like a map that it would build as its representation, which is real time, which is updatable, and which it can actually use to plan intelligent action. And the second, key hypothesis in that paper is that there's a generality to the sort of way that a spatial AI system would work. So whether you're building a drone to navigate through a forest, or a household robot, or an AR system for a headset, I think there are certain, major degrees of commonality between all of those systems in the way that they'll go about building a representation of the scene around them. So certainly they will have different parameters in how well they work, what the constraints will be, certain things they are good at doing and not good at doing. So, whether you need to deal with really fast motion or not, for instance, might be a big difference between a robot vacuum cleaner and a drone. But I think there'll be a number of sliders, let's say, 10, 20 parameters, which might define the key differences between these systems. But then that will be around a kind of common core of how these systems reason about the world. So those are some hypotheses which we can continue to debate. So something that I'll just mention here, which is a project I was involved in last year with some really interesting collaborators who are kind of big thinkers in vision and AI and robotics, was this project called Rearrangement, a challenge for embodied AI. So this is also a discussion paper. It's really leading on from previous work that some of the authors of this paper have been involved in thinking about challenges for navigation agents. This is saying, how can we take that a step further? So what would be useful challenges for embodied spatially aware agents in the future? And we came up with this sort of general description of tasks in terms of rearrangement. So an example rearrangement task is something like tidying up a room. So initially there's a set of objects that are in places they shouldn't be. An intelligent agent, a robot, with embodied vision, with some manipulation capability, arms. Its task is to rearrange that room into a tidy state. And actually, you can think of many tasks that robots might need to do in terms of some kind of rearrangement. Whether it's maybe constructing something. You've got a set of parts, and you need to essentially rearrange them into a structured form, which is building something. Or many other types of tasks, whether they're industrial type tasks or whether they are in maybe a more home type setting. So what we really did in this paper was to think about those sort of tasks in a general way and ask some interesting questions, like if we wanted to actually evaluate how good different agents are at carrying out tasks like this, we might want to think about certain things, such as how do we actually specify what the task is. So if you've got an agent that you want to tidy a room up, how do you tell it what the tidy state is? So that could be at some very kind of raw way, such as giving it a list of the objects and the coordinates you want them to get to. Or it could be maybe a more weak way. You could show it a picture of the scene in a tidy state. Or maybe you could even let it kind of just experience the world in the tidy state. So spend some time in the tidy room, build its own representation of what a tidy room is like, and then you put it into the untidy room, and its goal is to take that back to the tidy state. Another kind of interesting question we talked about is how would you evaluate the performance of a rearrangement agent? So clearly, a successful rearrangement means objects get to the positions where they're meant to be. How do you then put sort of metrics on all of those different objects? How close do they need to be to where you wanted them to be? Presumably, some of the things you might want the agent to do are not specific coordinates of objects. So say you've got you've got to put a plate on the table, and then you've got to put a knife on top of a plate. The plate could probably be anywhere on the table, but the knife has got to be in a certain position relative to the plate, for instance. So how do you specify things like that? And then there are other sorts of evaluation which we think are really important, such as how long does the agent take to do this, both in kind of the actual time and also in the kind of computational resources it requires. So I was really, I'm not a huge fan of sort of, benchmarking type things in general, I would say, but I was really kind of interested in this because I think that these rearrangement tasks motivate the sort of work in AI that I'm interested in, which is in particular persistent, real-time, updatable compositional scene representation. So I strongly think that you can't just train an end-to-end type reinforcement learning kind of agent to do tasks like this, or at least not in anything like the foreseeable future. There's just too much variation. I think successful approaches to this will start by building some sort of representation of the scene. So in my mind, something that's like the continuation of all of this SLAM type work that we've been doing, and then use that to do planning and carry out tasks. So I would hope that it would push more people to be interested in that kind of work. So mentioned within that paper are a number of existing simulation environments that people who haven't necessarily got access to robot labs can work with to actually do some research on these rearrangement type problems. So there are several already out there from different authors. There's actually one called RL Bench, which comes out of our lab, the Dyson Robotics lab at Imperial, led by Stephen James. So RL Bench is a simulation environment for robot tasks and robot learning in particular. So maybe if I just quickly show you this video. Really, the key point about RL Bench is there's a very wide variety of tasks, which are all implemented with the same robot. So you'll notice this is not at the moment a mobile robot driving around a room. This is a single robot arm routed to a desk. But I still think that there's a world of challenge in trying to carry out, so you'll see that most of the tasks this robot is doing, you can think of as rearrangement in some sense. It's putting books onto a shelf, it's building towers out of blocks and things like that. So this is an environment that you can download and experiment with. It's built on top of Copelia Sim, which is a free for research purposes robot simulator. And then RL Bench implements all of these different tasks within that environment that you can experiment with. And then the RL Bench simulates, different cameras in the scene. It gives you, depth and RGB cameras, either on board from the robot or also external cameras. And then everything is implemented with physics simulation. Yeah, so have a look at that if you're interested. Okay, so let's go back to talking about this question of incrementally building scene representation, which I hope that we've motivated in terms of how that's becoming this spatial AI capability that I hope will enable some of the tasks like this. And just to briefly remind you about some early work that we were involved in on those different layers of capability and maybe where we've got to now. So yeah, again, as Torsten mentioned, the first years of my career, in fact, this is even going back earlier than that to the work I did in my PhD in the 90s. But it was essentially, we were interested in feature-based SLAM. So we wanted to know where a camera was as it was moving through the world in real time. And we did that by building a system. So this is MonoSLAM, where we would detect and track and try and build a persistent 3D map of landmark points within the scene. We're using a joint probabilistic filter to estimate the position of those landmarks and the position of the camera, which is flying around in the scene relative to those. And we were able to make that work in real time as one of the first, pure vision-based SLAM systems. And then, work continued on that. Certainly feature-based SLAM systems got gradually better and better. But then a few years later, the next sort of big challenge was, could we go from sparse feature maps towards dense maps, which are not just purely about a map of landmarks to enable localization, but a map that would actually give us detailed information about a scene. And some of the early work we did on that was systems like Kinect Fusion and DTAM. This one, Elastic Fusion, which I worked on with Stefan at the Dyson Robotics Lab, was a Surfel-based system that could map whole rooms from depth camera information. It could close loops as well. So here you see we've got now a really quite detailed representation of a scene. This is actually my office at Imperial, which I haven't seen for in person for quite a long time now. So it's detailed geometric information, but what's not here is any sort of sense of semantic meaning. So that was really the next challenge, and very much, I would say, still an ongoing one. So semantic mapping, area of great interest. So the first significant work that we tried in that area to try and label a whole scene was semantic fusion, where this is, I would say, a fairly straightforward integration of a neural network which can label images with semantic segmentation. And here we fuse that with the Elastic Fusion system we saw just before, such that we're taking these multi-view semantic label maps and we are fusing them into our 3D Surfel map that's representing the scene, and therefore trying to apply a sort of semantic layer on top of this dense geometry. So yeah, that gave quite nice complete results. Maybe they look noisy in places. It worked better in some scenes than others, but that was seemed like a really real breakthrough for us at the time, and was our first serious work using deep learning as part of SLAM systems. So let's just have a look at a system like that. So I think a point I want to make is that by moving up through these levels of representation, what we've done to a large extent, I think, is just kind of thrown more and more at these problems. So in particular, we've used more and more computation, and in some sense more and more complicated systems and representation. So don't worry about what's in this picture here. This is just a kind of rough graph that I drew that represents the kind of data and computation structure of a system like semantic fusion. So I just really want to make the point there's a lot going on here. We've got different sorts of data images coming in, our kind of world model, our estimate of where the camera is. We've got lots of kind of blocks of computation, some of which are geometrical kind of loops of optimization to estimate where the camera is, for instance. Others are, the neural networks, for instance, which are supplying labels for images, which then get fused into the 3D model. The point I want to make is this is quite complicated. It's quite computationally heavy. There's a lot of data moving around here. When we actually implement this as a real-time system, it's running on a machine with a CPU and a GPU. There's lots of data kind of flowing around, and it's all quite complicated. So when I then think about where we want to get to with this, and applications that are really lightweight, like the pair of glasses, for instance, how are we going to how are we going to pack something like this down into a tiny amount of computation and make it, really efficient? So that's something I'm really interested in, and I think there are two kind of key lines of attack that we are focusing on. So one is about representation. So in particular, how do we get away from these very large representations? So for instance, in elastic fusion, we use about 5 million circles to represent the shape of a room. And in semantic fusion, each of those has a kind of distribution over labels. Very, very expensive sort of representation. So how can we attack that? The other kind of key area that I'm interested in is how can we work on this to what's going on in computing hardware, and how can we take advantage of new sorts of processors in particular that are coming along, which might be much more suited to this sort of computation than a sort of desktop computing system. So just to briefly say something about, SLAM meets deep learning, of course, something that all of us have thought about an awful lot in the last few years. I think there's an almost continuous sliding scale in the ways you could attack these problems between pure kind of end-to-end learned algorithms at one end and purely human-designed algorithms at the other end. I think the approach that nearly everyone who's actually building systems that work are doing is very much somewhere in between, modular kind of systems with elements of learned things within a structure of a human designed thing. So whether that's that you start with a human designed system and replace kind of modules of that with neural networks, or whether you start with a kind of neural network and gradually sort of lock various blocks of that into certain forms that force it to work in certain ways. I don't see too much difference between those two approaches, but these kind of modular systems are where we're going to be for a long time, I think, and just have so many advantages. We can sort of understand roughly how they work, we can debug them, and we can use all our previous experience from human designed algorithms to help the way that we now design learnable blocks of that. So sort of inspired by that, we've got a number of recent projects which I think are attacking this representation question. So how can we get over this, try and remove these huge representations? So if we think about something like the shape of a room, which I mentioned was represented with 5 million circles in elastic fusion. Actually, if you've experienced a lot of real rooms, you know that there's probably a lot less variation than that. So you can represent the interesting structure of a room with a lot fewer parameters than the parameters of 5 million circles. So clearly here we can do some machine learning, and we can try and look at a data set of rooms and try and learn what's typical about rooms, and in particular try and learn some lower dimensional embedding. So that's in particular what we were doing in the two papers that we had a couple of years ago, so Code Slam and Scene Code. So this architecture is a sort of autoencoder architecture conditioned on images, with the goal being that we know from a single image we can predict the depth of a scene, and we can predict the semantic labels of a scene. We also know that those are never perfect, and in particular they might have certain sort of systematic problems. So if you have looked at single view depth networks and there's a fairly textureless area, for instance, you may know that the network will know that that's probably a flat area, but it may not know very accurately what the depth and orientation of that kind of plane is. What we have in these Code Slam based systems is a kind of learned code, which is a low dimensional space that allows you to then optimize those parameters that come out. So we make a single view depth prediction, but it also comes with a code that starts at 0. But when we adjust that code, which might have only 32 parameters, we can sort of adjust the dense predictions. And then that allows us to do things like multi-view optimization. So we've got multiple images which observe overlapping parts of the scene. And by code optimization, we can do dense depth fusion, and we can also do semantic fusion in scene code. If you're interested in those methods, I would recommend looking at this paper led by Jan Zarnowski on the system called Deep Factors. So this is a kind of quite general real-time capable implementation of the CodeSlam type method. And just a quick kind of example here of what it can do. So we've got a stream of monocular images coming into this, but then we're doing dense depth prediction, but then this kind of joint optimization of the pose of the camera, and then of this code that's generating the dense geometry. And within a general kind of factor graph framework, that's able to produce, quite nice dense scene reconstruction. Okay, so have a look at that. So the latest project in this kind of general area that I'd like to talk about is one that we actually just made public last week. So this is a system called IMAP, led in particular by Edgar Sukar and Shikun Liu. So this is a quite new way to do SLAM that we're quite excited about, using the implicit neural representation, which is familiar to many people from papers like NERF. So here we're using in real time a multi-layer perceptron as our only scene representation. So let me just quickly show you a bit of video to explain how this works. So it's a real-time system, and we are training a neural network in real time here as the scene representation. So we're moving a depth camera around in a scene. So you know that these implicit networks, so I should say that a big difference between this and NERF is that we are using a depth camera, which certainly makes this a much easier problem. So just to explain what's going on here. So this implicit network is an MLP such that when you feed in an X, Y, Z coordinate, it will output the expected occupancy and color of a point in the scene. So now if we have a camera in a known position within that map, and we have a color and depth image come from that camera, we can optimize the parameters of the network such that when we render from the network, the depth and the color match up to what we've observed. So here on the top left, you can see the RGBN depth that we're observing live. And then here we've got basically renderings from our implicit network. And we are trying to optimize the parameters of our implicit network to minimize the difference between this RGB render and the real RGB image and the depth render. To turn this into a SLAM system, what we want is that we want to be able to feed it a continuous stream of images, but we want this network to converge to a meaningful map representation. And the way that we do that is to use a keyframe structure, which is actually in SLAM, if you know your SLAM history, it reminds me very much of PTAM, and we were inspired by that. So PTAM used a set of keyframes in a scene to represent the parts of the scene that you're interested in. And then there would be two threads in PTAM, one which is tracking the camera, and then one which is jointly optimizing the map representation and the set of keyframes. So here's just showing the kind of final reconstruction we get after kind of 2 or 3 minutes of scanning this room. But just to go back to this image here to explain how it works. So these red frustum shapes you can see here are the keyframes in the system. So as the camera's moving around, every time it's observing a reasonably new part of the scene, we save a new keyframe, and you can see the set of keyframes here displayed at the bottom. So the point is that if we were only ever just showing the network the latest frame and optimizing it against that, it has no sort of reason to remember the old stuff, and we would get this sort of forgetting problem. So what we therefore do is we keep this set of keyframes around, and then in the mapping thread of IMAP, we are kind of selecting old keyframes and always showing it some information from the old keyframes, as well as the latest information from the new live frame. And the way that we actually choose what information to show it is one of the real secrets to making this run really fast. So we're using a kind of sampling. So we never show it all of the keyframes all of the time. That would just be too expensive. We choose which keyframes would be most useful to show the network now. And then we also go further, and these red points here show we sample points within those keyframes. So we try and choose the most kind of informative points within each keyframe, which are going to most improve the quality of the map. So you put that all together, you can optimize the map at about 2 Hertz or something like that. So the map is ticking away, which is actually pretty much the same speed that PTAM's map update ran at. And then meanwhile, we're doing a live tracking thread that runs at about 10 Hertz, which is estimating the position of the camera, again, by rendering the implicit map and aligning against it. So the implicit map is the only scene representation. There's no like point-based SLAM system behind the scenes or anything like that. It's a pure implicit system. Here's just another example, which I think is quite interesting in terms of showing some of the characteristics of this. So obviously, this is a relatively low resolution scene representation at the moment, but it has very interesting properties of very quickly converging to the kind of main shape of the scene and then adding in detail later. So you saw that with this staircase, these kind of banisters were initially a kind of solid block that gradually got carved out. And then some of the great properties of this system are the way it can kind of complete shapes, even that it hasn't seen completely. So we're only kind of looking at this chair. I think maybe that point is clearest in this example, where you look at an object like there's this orange football on the floor here, which we've only really seen from one side, but the system kind of makes a shape for it at the back. So it will always give us a watertight reconstruction, and it often does that in what seems like a very plausible way. And to make clear again, this is a system that's never seen any training data. So there's nothing in this system which is specific to mapping rooms or anything. It's a pure sort of learning in real time system. So the only priors, if you like, that are in this system are whatever is built into the structure of the network that you're using. And we're using a very small vanilla MLP, but it has these really interesting kind of shape completion properties. Good, so that's interesting to me in particular because this neural network is so small. It's only about a megabyte of weight. So it seems like a very kind of interesting representation of the scene, which is sort of automatically discovering what are the right, most important parameters to represent the shape of this scene. When we're not sort of telling it how to use its weights to represent the scene, it uses them in seemingly an automatic and smart way. Yeah, good. So moving on from that, and in fact going back a little in history. So that system and the CodeSlam system are very interesting. They're certainly seeming to achieve this thing of representing the shapes of scenes with a smaller number of parameters used in smart ways, but actually in ways that are still quite hard to use for intelligent action because they're using these parameters still to represent whole scenes. I think a kind of long-term target that we're interested in is much more kind of composable or modular representations of scenes, and in particular representations of scenes where the objects really become the kind of key elements of a scene. And our interest in this goes back to work we did now about 8 years ago in this system called SLAM++, where we built this SLAM system that operated at the level of objects. So this was a system where we had prior models of a set of objects that we knew were typical in this scene. And the SLAM system worked by fitting those objects to depth data and then jointly optimizing the positions of those objects, the position of the camera. And it was very much like these objects became the landmarks in our SLAM system. So that was we've continued working on this idea and trying to tackle some of the weaknesses of this. Most obviously, the objects here are fixed and they have, we can only map exactly these types of chairs and tables in this system. So in fact, still with that basic assumption, we can go further, so a recent system we published called More Fusion, it still basically has this assumption that we're trying to make a map of objects in the scene for which we have strong prior models. But here we're going to show that that allows us to tackle this more, difficult case where those objects are actually closely interacting with each other. So here's a robot arm, and it's looking at this cluttered scene with a pile of objects in a box, and it wants to be able to, manipulate one of those objects. But in order to do that, it has to reason about the shape of all of those objects and their positions. So in More Fusion, we kind of jointly estimate the positions of this set of objects under the constraints that we know that real objects, they can't be intersecting each other. So I'll just skip forward a little bit here, but we build this nice representation, and where even some of these objects, are very largely occluded. So it would be very hard to estimate their positions, just if you were doing single object estimation. And then we can use that for robot manipulation. So we've got some demos here, which are, sort of rearrangement demos. We want to move this red box into this brown area here, but we have to remove some of the other objects first in order to do that. So that system is still assuming perfect knowledge of objects. So what do we do if we don't have, exact CAD models of the objects we want to map? So we could go all the way and say, what if we have no specific knowledge of the shapes of objects? All we have is a 2D kind of segmentation engine, such as mask-RCNN, which will tell us what are the separate objects in an image. And we showed in the Fusion++ system that we could use that to build a graph map of the objects in the scene, where each of these is a separable object, kind of like as a landmark in the scene, but we independently reconstruct the shape of each of those objects with like an SDF fusion method. And you can see that that's fantastic in that it allows us to deal with any type of object that we can segment here. But on the other hand, we only get this partial reconstruction because we're only reconstructing the parts of the object we can see. So something we've done recently, which is trying to sort of bridge the gap a bit between those two approaches, is what if we have, we have some knowledge of the shape of the object, but it's not as perfect as a CAD model. So if we have, in this system, we have learned prior models for certain categories of objects. So we have mugs, bottles, bowls, and cans here. So these are, we've never seen these specific objects before, but we've seen a database of many cups, many cans, and so on before. And we've learned a kind of autoencoder code type model for each one of those categories. So now at runtime, we can fit those models to our data, and then those models become landmarks in a SLAM-like system where each of these, so here we're jointly optimizing the pose of the camera, the positions of the objects, and then also these coded shape parameters of the objects. And we can then build these quite nice representations, which again we can use for manipulation. So here's a demo where the robot looks at this scene. It's fitting these shape models from just a couple of views. So even though it's only seen a couple of depth views here, it's able to fit these complete and quite accurate models, which are good enough to then use for planning and interaction. So here we now get our robot to pick up the bowls in order of size and stack them precisely. So this kind of question of manipulating objects, which is not just picking them up and dropping them, but is actually picking them up accurately such that you can actually place them accurately, I think is something that, yeah, more people will probably become interested in. And I think a lot of work on manipulation has just been about grasping and dropping. But most real tasks in manipulation, like tidying a room, you need to be able to place objects accurately. And that, again, for me, motivates, more sort of detailed and accurate work on scene representation. Okay, so I realize I'm coming towards the end of the time I should be spending, but I'll just spend a few minutes on this kind of last part of the talk. So this is, returning to the picture I showed you earlier of the scene, the graph of computation that represents semantic fusion. And I said the other kind of interesting line of attack is thinking about going on with hardware. So, there's a lot going on in AI hardware. One area we've been very interested in is what's going on in sensing hardware. And we did this work with an event camera, which for me is a signal of the way that camera hardware will be changing. So we no longer have to use cameras that were designed for photography, for computer vision. We could design our own ideal sensors for computer vision. And I think an event camera, which, as you probably all know, measures per pixel differences rather than directly intensity, and gives you this very kind of low bit rate signal, is a move in the right direction. But what I've become really interested in recently is what's going on in processor hardware. And this really initially came out of a project that I was involved in with colleagues in Manchester and Edinburgh, on thinking about this kind of co-design of algorithms and hardware, and how well do different sorts of algorithms work on different sorts of hardware. And we produced in this project a tool called Slam Bench, where you can run the same SLAM algorithm on anything from a large desktop GPU down to a tiny embedded board, and really think about, what's the computation, what's the data flow, what are the memory requirements. And so towards the end of that project, new things started to happen actually in commercial processors. And various companies are interested in building, processors that are really designed for AI workloads, and would argue that, we've been using CPUs and GPUs. Those were not really designed for AI. Of course, GPUs are the big thing at the moment. They work pretty well for certain types of things. So for dense reconstruction, we use them in all those projects, elastic fusion and so on. And then of course for CNNs, they work really well. But machine learning doesn't have to be a CNN. There could be all sorts of much more complicated, maybe graph-like topologies, which don't necessarily work very well on GPUs. And maybe we use CNNs so much just because they do work on GPUs. So what if we could think more flexibly? So a particularly interesting concept is a graph processor. So this is a picture from a company called GraphCore in the UK, which is a new company designing a chip called an IPU, an intelligence processing unit, which it has a very massively parallel architecture, a bit like a GPU in that regard. But what's very different is the sort of parallelism that this allows. So rather than all of these individual cores having to be doing the same thing all the time, like a GPU, each of these can be doing something completely different. And then it has a very high performance kind of all-to-all interconnect structure. So the sort of algorithms this is good at are where each of these cores are doing something quite different, and then they're passing messages between them. And I think that's pretty exciting, and I think that's representative of where I think hardware is going. There'll be a lot more chips that work in this graph-like way, but also if we think beyond chips towards a future of many kind of edge type smart devices that might be communicating with each other, I think we'll also have this quite general graph-like structure. This is a nice visualization from GraphCore of how, if you take a certain algorithm here, it's a standard neural network, you identify the kind of graph-like patterns of how it communicates both during training and inference time, and you kind of compile that down onto a graph processor to make it as efficient as possible. So a bit inspired by that picture, and this is very much the sort of thing that's discussed in the first future mapping paper, I've become interested in thinking about spatial AI problems, thinking about the graph-like structures that are present in the data stores that we use and in the computation that's done, and thinking about how that could all eventually be mapped down to a sort of graph-like processor, which I think would have big advantages, for efficiency in particular, because what we really want to get away from is shuffling huge amounts of data around our processors. What we really want to move towards is much more, the processing and the compute in a system are much more co-located, and the processing happens locally on data, and then messages are passed between those systems as needed. So in the second future mapping paper, I really look at this question in more depth and think about what the properties of algorithms should be that can do this sort of computation. And a really interesting term is factorized computation. So this is really moving away from thinking about how computers work as following a sequence of steps towards thinking about posing a problem that you would want a computer to solve as a kind of graph of constraints where there's data and computation kind of implicit in that graph. And then you can lay that out on a parallel computing architecture with message passing and try and solve it in that way. So in particular, in Future Mapping 2, we identify the old, but I think surprisingly not very well known or underused algorithm of Gaussian belief propagation as really a very general framework that I think could tackle an awful lot of these problems. So we've done some concrete work already in that area. So last year at CVPR, we showed for the first time that you can do bundle adjustment on a graph processor using Gaussian belief propagation. So essentially what we do is we take the factor graph that represents a bundle adjustment problem, and we lay it out in really a very simple node-wise parallel way on a graph processor. So let me just skip forward a little. So we've got our factor graph for a bundle adjustment problem where we have nodes for cameras, we have nodes for points, and then we have factors representing the kind of measurements between them here. And then we have the parallel cores of a graph processor, and we literally map them across. So those nodes are laid out in parallel on the graph processor, and then there are these connections between them. And then we can solve bundle adjustment, therefore, by belief propagation, where we basically have to do computation in parallel at all of the nodes, and then we pass messages between them. So this little animation shows that we have different phases where we calculate messages in parallel, and then we pass messages from factors to variable nodes. We update the beliefs at the variable nodes, which is done in parallel, and then we pass messages back to the factors. And you iterate all of that, and amazingly, it converges, and it gives you, the same results as you would get from Ceres on the CPU, but it can do it really, really fast. So this algorithm takes quite a lot of iterations, but the parallelism you can harness is absolutely enormous. So the graph core IPU we used has over 1,000 cores on a single chip, and therefore we can run the whole thing very fast, and we're showing very, very fast bundle adjustment. So that's just the starting point of research in this area, and I've got lots of stuff going on in trying to take these ideas into more other directions for different sorts of processing, for front-end image processing, for graph maps that gradually self-abstract themselves into more abstract forms, for multi-device distributed mapping, where we lay out these graphs across multiple communicating devices, and then also some interesting ideas of how we might implement general learning architectures within this sort of computation. Okay, I'd better finish there. So just some conclusions. So spatial AI research, I think it's exciting. I think we're going to be doing it for a long time yet. So some interesting things to work on include efficient 3D scene representations and systems for incremental scene understanding, co-design of processors, sensors, and algorithms, and integrated graph-based algorithms for estimation and machine learning. And just to mention my affiliations, so I lead the Davison Robotics Lab at Imperial College, which is an academic lab with postdocs and PhD students working on these topics, particularly around scene understanding and manipulation. And I'm also co-founder at Slamcore, which is a London-based startup supplying applied spatial AI solutions. So thanks very much. I'll stop the screen share there.
Thank you very much for the great talk. I found it very inspiring. So typically we start like a panel discussion here, but there's a couple of questions on YouTube. So maybe we start with those. Both are about IMAP. So the first one was, does the IMAP network only keep track of the implicit function, or is it the entire mesh reconstruction? So for example, probably using marching cubes used for the optimization.
So the main algorithm of IMAP is only updating the implicit function. So the implicit function is the master scene representation, and that's used both for tracking and mapping. So of course, if we actually want to see what it's doing, then so in the videos I showed you, we are at some regular interval meshing the implicit reconstruction in order to produce the visualization. So that's not really part of the main algorithm, but it's actually quite an interesting thing about this method, that visualization is not necessarily easy to get. So actually, we actually in our current demo, we have a second GPU which is used every so often to do meshing so that we can actually see what's going on, but it's not part of the main algorithm.
Do you think it would make sense to actually optimize over a mesh instead of an implicit function?
So your audio dropped a little bit, but you said, would it make sense to use a mesh?
Oh, sorry. Yes, to directly optimize over a mesh versus an implicit function.
Well, of course, there are many representations we've thought of using for SLAM, and at various times we've thought of directly doing SLAM on meshes. Actually, that's very hard, and we probably have never quite figured out how to do it, because the difficult thing about a mesh is that as topology changes, and as you get new measurements, you essentially need to do kind of editing type operations on a mesh. So yeah, we've never really figured out a way to do that. So yeah, all different 3D representations have different pros and cons, I think. So these implicit functions make things very sort of simple in some ways. So whether it's an implicit function represented on a grid like an SDF, or whether it's this implicit function represented by a network, you can kind of query and update it easily. But on the other hand, for instance, it's quite hard to render the whole mesh efficiently. So I would say at the moment, we're not saying this is the one and only way to do SLAM. I think we're exploring the space of possible ways to do it. And frankly, I was quite amazed that it works as well as it does, this entirely kind of unstructured MLP and also just how fast you can actually train it to do something useful.
Yeah, I completely agree. I was very surprised when I read the paper that you can actually train the network while doing reconstruction real time. I didn't imagine that this was possible. There's a couple of more questions, but I think they all go in a more general direction. So Stefan, please feel free to join in. And if we move away from those questions, that's completely fine as well. The first one is, keeping with IMAP, how does it scale? Does it scale, and what would be needed to scale it to larger scenes?
Yeah, it's a great question, and I can't say that we have really investigated that yet beyond a sort of a room size model. So if you did want to map an area that was either much bigger or much more detailed, presumably you do need a bigger network ultimately. Yeah, I don't even really know, to be honest, how close to, we're using a pretty small network, 1 megabyte of weights, how close we are to sort of maxing out the representational capacity of a network like that. I don't really know, to be honest. I mean, it would be quite clear that if you did want to scale to map a building or a city, clearly there are a pretty well-known set of steps from SLAM that we could follow. We could build a graph of local maps, and we could do all the usual loop closure, detection and optimization. If you wanted a more sort of unified map, I'm not sure. So for instance, thinking about loop closure is interesting. So certainly, we showed this kind of room scale map, and yes, the camera does come all the way around and closes back up, but I think there's relatively small drift. But we didn't. It's not like we're trying to close a big error. So it would be very interesting to see if you did have a loop that was big enough that there was reasonable drift, and then you were able to kind of close across that, and then you kept optimizing. Would it do the things that we hoped that a SLAM system should do on loop closure, which is to, bend the whole map round in the correct sort of way? I'm not sure. So I think that's all for future experimentation.
Okay, so then if I may jump in here. So first of all, thanks a lot for having me here. It's been, of course, a pleasure hearing also some of the work that I haven't been involved in. And so maybe I can just ask some questions around that. Because a lot is about representation, right? A lot is now about how do you represent the 3D world. And I think you've shown, Andy, a sort of continuum from online reconstruction all the way to recognizing objects that are known and pose estimation and kind of all kinds of things in between. Yeah. So perhaps an interesting question in that area, related to previous questions as well, is how can we sort of unify that? That it seems a lot of the times it's kind of either we pre-learn things or then we reconstruct at real time. And then if we try to do it simultaneously, then we, for instance, we might lose some of the accuracy. So if we do things like code slam, you can do a lot with kind of pre-learning and online optimization, online reconstruction, but you sort of seem to lose some of the accuracy. And then at the same time, when you do live reconstruction only, you don't benefit from any of the previously learned stuff. And that even applies to IMAP, which is also basically an online reconstruction system. So the question is a bit, how do you envisage, can this be solved? How can we bring back accuracy if and when we need it from the online reconstruction kind of stuff that we know, and at the same time leverage all kinds of pre-learned stuff in all shapes and forms?
Oh yeah, no, great question, of course. Yeah, I mean, I don't know the answer to that. I feel clearly, yeah, we need to bridge both learned and kind of live information. So I guess, we've understood very well the limitations of both of those. I guess going back to, the work we did on semantic fusion, where we were maybe always slightly disappointed with how, you've got this system that's learned semantic segmentation on a standard data set, and then you pick up your camera and you point it at things in your own room, and it doesn't work as well as you would hope. But on the other hand, always having to train from scratch in one particular environment, I guess this sort of scene specific learning that IMAP does, for instance, and we might put semantics into that sort of system as well. That also has many disadvantages. So yeah, I always try and imagine, a robot of the future that you buy and you bring it into your home. What would be reasonable? You would expect to turn it on and immediately it starts doing something sensible, but I think it's also fairly reasonable to expect to have to teach it a little bit. Maybe similar to the amount that you would have to teach a human who would come to your home to do some kind of work. You would probably have to explain to that person. You might spend half an hour with them pointing out certain particular things about your house, for instance. That seems kind of reasonable. So now sort of balancing that prior information and the new, scene specific information, of which there'll only be a small amount, I think. I guess, as a Bayesian, it feels like we know the right way to sort of find the balance between prior information and new information, and that, assessment of the uncertainty of those two things should show us the right way to balance them. But I feel like the frameworks we have at the moment in deep learning especially are not easy to use in that kind of proper Bayesian way of really having proper knowledge of how uncertain they are, such that you can then weight them against other information. I think that's very tricky still at the moment.
Okay, so some open challenge. I mean, and perhaps also, I mean, this is another aspect of that. I think we are sometimes a little bit extreme in our thinking, as in it has to be either one thing or the other. And perhaps, I mean, this is just an idea. A robot or so, for instance, might also do both sort of in parallel. So maybe this is something. I don't know what you think about that concept of exploring sort of running several concepts with all their pros and cons in parallel. That's perhaps a sort of practical approach to that problem. But then again, maybe it's also something that we do as well as humans, and we have sort of several representations and abstractions that we have in parallel.
So yeah, I mean, I showed these various systems, but clearly we could build that sort of joint system. Let's say, you know, Fusion++ that also has the kind of coded node SLAM object, that also has a CAD object recognition capability, and then maybe also has a more sort of non-structured, maybe a code SLAM capability to fill in the background that's not object or something. And this sort of idea of it doesn't seem very satisfying in some ways, but a sort of hierarchy of discrete sort of representations that, you know, with an object, you might initially you just get a bounding box from a, but you think this is a separable object, but you don't know what it is. You start reconstructing it, you know, bottom up. At some point, you recognize its category, and you're able to upgrade it to a sort of, you know, shape basis type object. And then maybe later on, you recognize, oh, it's actually this specific CAD thing that and you replace it with that, and different objects in your scene may exist at different levels of that hierarchy. That's a system we can imagine building. I think it would be pretty complicated, and it in some ways doesn't seem very sort of theoretically satisfying. But I think if you were trying to maybe build the best sort of object SLAM system you could right now, that might be the approach you would take.
Yeah, because that also relates to the question of perhaps then in a more robotics context, for instance, or also VR application context, what is even then the right representations for that, and even within that context for a specific task. So I guess there's also, you would agree, quite a lot to explore, and it's probably open questions. What is really the best for specific tasks?
Yeah. And even though I've talked, you know, about robotic applications and rearrangement and things, we're probably just at the beginning of actually thinking about, what representation actually really enables those tasks. So it's quite clear, for instance, if you're a robot and you're driving around and you just want to avoid obstacles, that requires, you know, much less detail in reconstruction than if you're going to manipulate objects. But on the other hand, if you're going to manipulate objects, do you need that sort of millimeter precise representation? Maybe for certain types of manipulation you do, but maybe if you've got something like, you know, a deformable blob gripper that can just sort of more or less pick up anything, then maybe a pretty rough idea of the shape of an object is enough to do lots of sorts of manipulation. Yeah, I agree completely. I think we're just at the beginning of really integrating this kind of representation work with planning and thinking about what could really be done.
I think in this respect, the implicit representations are interesting because you don't force a resolution on the reconstruction. But I mean, on the object grabbing example, you first, I mean, as long as you're far enough away, you just need to have a rough guess of the shape, right? And then once you get closer, you can refine that.
So this sort of just in time reconstruction or something that you're while I'm not looking at this object, it exists in my map as a pretty abstract blob somehow. But then when I turn my attention to it and I'm within the next second I need to pick it up, then I do the best job I can to reconstruct that from the data I've got. And that feels a bit like our experience of a human vision, doesn't it? That as soon as you turn your head away from part of the room, it sort of seems to fade down in your representation to something much more abstract. You don't forget it completely usually, but but it feels like a sort of graph of blobs or something. But then you know enough about it to know where to look back and find that object when you need it. And then your sort of high-res thing kicks in, and then you can do something detailed.
Do you think then, like, you can get a representation like this in the sort of IMAP entire scene encoded into a code implicitly, or do we need an explicit structure for the objects in the graph?
Yeah, really interesting. Yeah, we haven't really thought about that yet, but yeah, this idea that a sort of compositional structure of that model might just emerge by itself. I mean, I think we're already seeing a little bit of evidence of that in the way that IMAP works. So, for instance, there's in the first part of the video, there's a ball on the floor like a football, and I already mentioned that it seems to sort of complete itself quite nicely. But one of the things you'll notice about the IMAP model is it's sort of wobbling a bit all the time, and it's being optimized using some kind of stochastic gradient descent type method. So the weights are all kind of changing a little bit all the time. But I think if you look at the football, you'll see at certain points the whole sort of shape of the football sort of vibrates in quite a sort of unified way that for me indicate that the shape of that ball is generated by not many weights in the network. So if all the weights were kind of changing randomly, and if there were 1,000 weights that were generating the shape of that ball, it would seem very unlikely that all of them would wobble in a coherent way and you'd see the whole ball of the shape of the ball change. But if the main kind of elements of the shape of that ball are generated by just 3 or 4 weights in the network, it's I think we can sort of see that by the way that it sort of oscillates in a fairly coherent way. And so yes, I think the network for itself is discovering, it's trying to discover the most efficient way to represent the scene, and that inevitably I think means that it represents simple parts of the scene with not many weights in a way that's getting a little bit close to a sort of a segmented or an object-like representation. But there's no reason that sort of compression would relate to our concepts of objects and the names that we would give them necessarily.
So that's really interesting. If I may, the question then also around, and I think you touched on it already, what happens if you do loop closure, for instance, or you could extend it towards what happens when there is motion that you might want to track in the scene. If you're, for instance, if you keep reconstructing while you're actually manipulating, for instance, rearrangement task or so, do we think, is the hypothesis extending to that a kind of implicitly a efficient representation is learned, such that by just changing a couple of the weights in the network, you can also change and rearrange basically these objects or deform a scene to bring it into a loop closure. I mean, I guess there's a lot of guessing here, but that's ideally where we would want to get to. Right?
Yeah, that's right. Yeah, and I'd love to investigate things like that. I think there are certain details that are probably really important. So like this positional encoding that we use in these implicit models. So that we do something similar to NERF in IMAP, where we feed the input coordinates into these kind of random sign type functions, and that will say a lot about how one weight affects the kind of how many the locality of the things in the scene, or the more global nature it can affect. And maybe there are designs of how that input encoding could work that might give us much more that sort of property you were talking about, Stefan. Yeah, I can't really imagine at the moment that there's a small number of weights that would, for instance, produce the overall kind of bend of a room that you need to do in loop closure. But it might be that you could, through a different design of the positional encoding, you might be able to achieve something like that. Yeah, very interesting.
Okay. Yeah, I mean, do we have other questions from the audience or so? Or I mean, I have tons of questions anyway. I can ask more, but
There's a few other questions on YouTube. We can ask them, and you can interject with your other questions. So, switching topics somewhat, there's also a question regarding the rearrangement problems. So, the problem of rearrangement, there seem to be indirect effects due to interactions between the objects and the environment. And do you think these effects should be explicitly modeled?
So, indirect effects. So I'm just trying to understand what that question is getting at. So clearly, a lot of rearrangement tasks are not just object A to position B and object C to position D, and all those things could be done in any order. I think most interesting rearrangement tasks, there is this strong interaction between objects. So let's say that you need to build a tower out of objects. So there's 5 blocks laid out on the table, and your goal is to rearrange them into a tower. Then clearly things about the order that you pick up the blocks will make that task easier or harder. So if one block is the biggest, it would be sensible to do that object first. So I definitely, that's what I quite like about the rearrangement task, is even if your goal is just to build the biggest tower, and the only metric is how many blocks high do you manage to make the tower, that motivates quite subtle kind of intelligence and planning, I think. I.e., unless you're picking up the biggest block first and then the next biggest, then you're probably not going to ever be able to make a tower that's 5 high. So you don't need to be very specific about the specification of the goal in order to motivate quite sophisticated behavior. So another example might be, let's say you've got to fit a set of books onto a bookshelf. So there's a bookshelf of a certain size, and you've got a number of books that sort of just about fit in. If you placing the first book is pretty easy. There's loads of space, but unless you place the books carefully at the start, then you'll run out of space and you won't be able to place the last one. So if you know right from the start your goal is to get as many books on as you can, you would presumably want to place the first book, carefully in one corner, and then place the second book next to that, and maybe even push it up against that to make sure there's no gap. So I don't know if I've answered the question exactly, but those are some of the things that made me think of.
Maybe a somewhat related but broader question. So what's your take on how much you need simulation to learn these kinds of tasks, like rearrangement versus imitation learning from real examples?
A question where I think there's always back and forth. And I think I've probably come from the background of, trying to do real robotics and had a sort of natural suspicion of simulation, but actually have been pleasantly surprised recently, I would say, by what can be learned in simulation and usefully transferred to the real world. And of course, mainly simulations have been getting better and better, of course. There are certain things which I think definitely already work quite well. So simulating, appearance and, rendering, all that stuff's getting better and better. I think if you're simulating, shape, for instance, to simulate depth camera images, that works really well. Even better than simulating RGB, because there you have all the lighting effects that are a little harder. What still seems really hard to simulate well is the sort of, the hard physics of things like contact and friction and pushing. So if we're in a rearrangement task, you want to place and push and slide objects and poke them into small gaps and that kind of thing. There, it still seems to me that the simulations are not good enough that you could expect to train something purely in simulation and expect it to work on a real robot. But maybe as a general point, I think simulations are getting better and better. Of course, physics simulation will also improve. And the amount of sort of specific training you might need to do in the real world, I expect will gradually go down. I guess that's my general view about it. But I think we'll always need some.
So I have a sort of follow-up question a little bit in that space. I think a lot of the work, especially from the deep reinforcement learning community, and that includes, I guess, the RL bench simulation work, is to do with a relatively constrained setting and a fixed arm doing something. And, you know, to put it a bit more controversially, I would say the RL people would tell you don't need SLAM. But then also they largely solve these types of problems. So I guess the question is a bit, to what extent should we pose problems and do simulation beyond this kind of bit more classic setup where perhaps the conclusion, at least to date, is right, that you don't need SLAM. You can just use your live sensor data to do quite complicated stuff.
Yeah.
Yeah, how do you see this?
Yeah. Really interesting. So, you know, a number of the other projects that are kind of linked to in the rearrangement paper, you know, do actually have agents that move around in rooms, you know, and also have arms. So this kind of mobile manipulation setting. Yeah, and of course I agree that brings in all the challenges of SLAM. I suspect that, yeah, there may be a lot of people that would work even on those problems and might just sort of assume that the SLAM part works, you know, i.e. read off ground truth robot pose, or just assume, there's something out there that will just solve that for me, and that's not really a problem. Whereas I don't think that's really the case. I think we always find that, you know, even if you have a robot that's moving around in the same room all day, for instance, just that tracking problem is still kind of a hard one. Yeah, so I think, yeah, we do need to think about moving around. So yeah, I still think there's plenty of challenge just in dealing with things with a fixed arm on a base, like RL bench it does at the moment. But yeah, we should think about moving around in more general scenes as well. Yeah.
Okay. Probably agree.
So there's another interesting question on YouTube, which I'm going to somewhat interpret because I think it's a little bit vague. So is it possible to completely remove the requirement on CAD models while addressing SLAM at the category level for objects for unseen instances? I think generally, is there a way to encourage generalization to novel classes or categories with these kinds of graph-based or implicit models? That seems to be a task that people can do quite well.
Yeah, I think dealing with more general sorts of objects is still really, really hard, and I don't really have a good way into that. I look at an object like I don't know, something like a bag. Let's say it has many parts. It's kind of flexible. You know, there's thousands of different sorts of bags. So I don't think something like a simple shape model is going to work well on a bag. This, you know, yet a human can look at a bag and effortlessly understand the shape of it, the different parts, you know, the function of the different, you know, pockets and handles and everything. So these sort of methods that can, you know, decompose a structure into its parts, those seem promising to me as possibly the right way to go. But yeah, I think where we want to get to in these sort of spatial AI representations is we would ideally like to represent everything of interest in a scene, in a room, with a, you know, a small vector of numbers, I feel like, for each one, you know, relative to some prior training data, I assume. And yeah, for these objects that are quite simple in their variation, the shape of a cup, for instance, okay, that's already working reasonably well, I think. But I to be honest, don't have much idea yet how to do that for more more complicated objects.
As always, many more tasks to full spatial AI.
Yeah.
But this you've already mentioned, I think, at the beginning. I think we're getting a bit short on time. Any last questions?
I mean, I would have some probably longer ones, so I'm happy to leave it at this.
Yeah, we can have a chat anytime, Stefan. So let's do that.
All right. Well, thank you very much for having this great talk, and thanks, Stefan, for the great discussions afterwards. So
Pleasure,
we'll
again.